looking at perhaps the most important topic of the course, energy transformations or conservation of energy, meaning that, as you can read yourself, that energy cannot be created or destroyed, only transformed from one type to another. So what I mean by that, if we look at a few examples, imagine you drop a water balloon from your bedroom window onto your sister, and she's on the ground below. Well, the energy transformation on the balloon starts with gravitational potential because you're holding it up high, so it's got some potential to speed up. As you let go of it, it loses gravitational potential and it gains kinetic energy, it gains speed right before it hits your sister on the head. Another example might be a sandwich in your belly gives you the energy to walk to school. So you've got in your belly, now if you just ate, actually it's just sitting in your belly. But it's when it's the sugars and the fat from it are in your cellular system, in your body, that your cells turn it into energy. And that's a chemical reaction. So that's what the chemical energy is. And it turns into kinetic energy, which is your motion, plus thermal energy, because you get kind of hot when you start to walk. The more you move, the hotter you get. So that's the thermal energy, and that would be the idea of the transformation, the energy transformation. Turning on a light switch. So in the electric circuit system, you've got electric potential energy, right? But that energy isn't doing anything for us until you open the switch, allow the electrons to close the circuit in the light bulb, creating light. Well, you've got light energy, obviously, and we talked about this earlier, that gives you thermal energy as well. So the energy transformation is electrical potential energy to light and thermal. Okay? Now the great thing is that we can do lots of calculations related, great for me anyway, maybe not great for you, but that we can do lots of calculations with energy transformations. It's possible to make calculations with respect to all energy transformations. In this physics class, we leave that very focused on gravitational and kinetic energy. Okay, you can do it with them all, but we keep it limited to just those types, and those two types together have the term mechanical energy. So here's our example. As Luke drops from the scaffolding after his fight with Vader, do you remember right after Vader says, "I'm your father," and he sort of jumps instead of going with Vader? He falls 425 meters in with no air resistance before reaching the tunnel. Now, I just realized the huge flaw with this, of course, is that he's not on Earth. And so because he's not on Earth, using 9.8 for G is not correct. So forgive me for that. I forgot. I wasn't thinking. But on the studio, he would have been on Earth. So we'll pretend he's in the studio on Earth. I do have a little, just to remind you what goes on. There's poor Luke.
Come with me. It is the only way.
And there he goes. He's accelerating as he falls, even though, and by virtue of that sound, it sounds like there's air resistance, but we're pretending there's none. Dropping his 425 meters before he starts to slide. Okay? So that's Luke falling. That's the question, pretending that he's on Earth. I can't believe I didn't think of that. So first we identify his energy transformation, which is he's got gravity potential energy because he's up high. It turns into kinetic. And here's how you do the calculation. We say, well, he's starting at 0. We want to find his speed just as he starts to reach that part when he starts to slide down the tunnel. So we want to find his V2. Oh, crap. I just realized that I used 400. In the calculation, I used 450. So we're saying height 1 is 450, height 2 is 0. Okay? Because always the lower height is 0, if you keep that in mind. So we're saying he's dropping from 450. It's not like he's on the ground when he hits a tunnel, but in the question, that's the bottom part of the question. So that's what we use. So the way the equation works is, this is really the equation you can use in these cases, and then just depending on what you're looking for. Okay, so I substitute in 9.8 and 450. I'm solving for V2. I multiplied those and then I multiply by 2 to get rid of this. And then you find V2. It's a fair bit of algebra, but there's some easier equations that come out of it. Okay, so by the time he hits that tunnel, he's apparently going 300 kilometers per hour, 94 meters per second. Pretty fast, which is fast, but considering he's not even on Earth, probably the G is nowhere near 9.8 on the little island of Lando Calrissians there. Ashamed of myself for that. Okay, another example. Ferd tosses a banana straight up into the air. It leaves his hand with a speed of 8.8 meters per second. Somehow he knows, right? There's Ferd. That's a visual approximation of Ferd's hand. I'm not supposed to give you any pictures of Ferd, but there's a visual approximation of his hand. Leaves his hand at 8.8 meters per second. It goes straight up. And the question is, how high will the banana fly before starting to fall again? So this time, our energy transformation, he's got kinetic when it leaves his hand, but at the top where it stops, it's not kinetic anymore, right? It stops to turn around and come back into his hand. And up there, it's just got gravitational. So you take, again, here's our base equation. You can substitute, the m's cancel, so you can just get rid of them. They show up on each side, on each term. I can tomorrow in class, if you want, or next time in class, or when you start working on this question, I can help you give you some rearranged forms of all these equations, by the way. Anyway, so you substitute in the numbers. This time Ferd is on Earth. We have to assume at least Ferd's on Earth. We don't know where on Earth, but on Earth. And we want to solve for h this time. How high does it go? Okay, so you just go through the process, and he throws it 4 meters into the sky, which isn't very high, but who said Ferd was strong, right? Okay, so again, what I've done there is I've said all the kinetic turns into gravitational. So kinetic turns into gravitational. You sub in what you know, which is the initial speed. Like I said, the m's cancel. And you end up with just height over here. You have to get it by itself. So you divide both sides by 9.8, and that's how you get the answer. I got a roller coaster question as the last. Here we're talking about the first drop on the Leviathan. Now, one thing we typically do with these roller coasters is we assume that at the top of that hill, it's got no speed at all. You know, it's moving a little bit, but we assume none just to make it easier, okay? And we want to know how fast is it going at the bottom of the hill, and which is also known as the maximum speed. So the energy transformation on the Leviathan then is gravitational turns into kinetic. There's our formula. mgh becomes 1/2 mv squared. So all this energy equals this energy. And here's the formula when you cancel again. You can always almost always cancel the m's out of these. Okay, fairly consistent rule. And it's just a matter of rearranging it to get V2 by itself. Okay, again, if you need me to help you with that when you start working on some of the questions, I would definitely help you get the rearranged forms. But this is all I'm doing is I'm substituting the numbers, right? G is 9.8, H is 86. Multiply both sides by 2, rearrange, and you get 41 meters per second, which is the maximum speed of the Leviathan. Multiplied by 3.6, that's where that came from. And I know that's a good answer because we could Google that. We could Google that, maximum speed of the Leviathan. Let's see what it says. (148 kilometers per hour). Yeah. Now there, see it says 93 meters. You might say, well, oh, what's the difference? Why is it? That's because that's 93 meters off the ground, right? But we're talking about the drop of the Leviathan. And that's what we care about in these questions, okay? So very specifically the information. When you do your roller coaster, you'll do this calculation on your roller coaster, and you'll have to look at your biggest drop, right? And you'll be looking at the drop. You won't be looking at the height above the ground. Okay, so that's it. That's all the lessons for this unit. I want you to do some of the assignment stuff. Then you can start working on your roller coaster soon.